All right. So guys, we had a chance yesterday to introduce day three. This was over writing function rules, and this was kind of tricky. I tried to explain this to where a function's like a machine, right? So when you set it up, you have to have, if you're going to set it up like an equation, you have to have an input so you can plug something in, right, to get an output. So they're built on inputs. X is our input, it has to be involved so that when we plug something in, like 2, you get an output. What was something maybe that was a little bit confusing for you as far as how functions worked and how they worked as equations?
The wording.
The wording?
Yep.
I can see that. Are you talking about the wording in the problems or just the wording for the equations themselves?
And the problem.
Okay, no, that makes total sense. I gotcha. So quick recap. We know we're going to have 2 variables. We're going to have our output, which would be like C, number of CDs, and we know we're going to have our input, months. And so, for example, on number 1, so close. For number 1, we know that the number of CDs, what's it going to be based on?
How much you got, stuff, your months.
Yeah, it's going to be based on the number of months that pass, because with each month that passes, what happens? Yeah. So we would say this is a function of number of CDs based off the number of months that go by. Just like down here, number 2. What was the question? How much would it cost? So cost was our output. And what was the cost based off of? The number of V visits in a year. Yeah. You see how we have a function that's an output based off our input. So V was our input, X. So we obviously had a chance to practice some of those too. So what I want to do now is, Shelby, I want to jump over to page 13. Yeah, and so I thought, why don't we do maybe 1 or 2 of these together, and then I'll give you a chance to maybe try one of these or a couple of these by yourself. Let's look at number 1 together. Take a second to read that. Always, these aren't long word problems.
Yeah, the long ones are hard. The short ones are easy.
That's understandable. Take a few seconds to just read. It's a 1-sentence statement. All we're going to do, Shelby, is write a function rule. We're just going to write the rule. We don't have to plug anything in. Just write the rule.
So that's what we did on the page.
Yeah, at the very top. So what's the first variable you're thinking here?
P.
P, the price. That's the total price. I'm thinking that's going to be our Y. That's going to be our output. Our Y, our output, whatever you want to call it. What's price going to be based off of, though?
Topping.
The number of toppings, yeah, for each topping T. So T is going to be specific when you label these, the number of toppings, yeah. So I mean, you don't have to, because they actually already gave us the label, didn't they? But here's the thing, Shelby, the reason I label it is it actually makes the problem easier. If you know what you're looking at, it helps you come up with the equation easier, because you're like, oh yeah, that would be attached to that, because that's what the variable means. So the right, if you know what it stands for, it's going to help you be like, okay, these numbers are going to go together because that's what that's talking about. If you just say topping, you could think, well, maybe, are we talking about the price of the topping? Are we talking about how much of the topping? Be specific. We're not talking about the price of the topping. What does T represent for? That's the number of toppings. It's very different than the price. Our T does not represent the price of the toppings. It represents the number of the toppings. And that's important, because that means we're going to know what to attach to it, the price per topping. So check this out. We have price based off the number of toppings, P of T. What are you thinking over here? What's our equation going to look like?
3, 9, 5, 6.
So close. So that's what the ice cream is by itself. And on top of that, what are we doing?
Add 85 cents.
And we're adding 85 cents.
Topping.
So how are you going to represent that? 0.85? We're going to add or multiply the T? We're going to multiply that T, because it's 85 cents times the number of toppings. Yep. And so you guys have a function rule. So what I'm going to let you do is I'm going to let you try number 2 and 3 for me. Go ahead and try these two guys. Again, label if you need to, and then we're just writing our function rule for these two. So go right ahead. So we know on number 2 that our earnings are a function of the number of hours. In other words, the money you make is based off how many hours you work, right? And what'd you end up getting for number 2?
$7.25
Yeah. We get paid $7.25 an hour, so you multiply that by the number of hours you work in, and that's going to give you your rule. Nice, short, and simple. Number 3 is not too different, but with one extra thing. We've got a plumber's fees, how much they charge, is based once again off the number of hours they work. But there's also something else in here. What's going on here, Shelby?
$75 for a household.
So in other words, just to come out, how much are you paying?
$75.
Yeah, if for them to even come out to your house to work, it's $75 right there. And on top of that, what else are we doing?
$4.50 times 8.
Yeah, then they're going to charge $60 an hour. Man, being a plumber, you make really good money. And they're in high demand. There are not many people who do that. So yeah, you are making some good money. Guys, if you need to, go to trade school, become a plumber. Get that done there. And so I actually want to do this next one with you guys. This one's going to be a little bit tricky. So once again, we're going to let's read over for a second. This is a 3-sentence one. Ooh. And look at what they want us to write a rule that represents J, which is Jose's age. Now wait, what's his age going to be based off of? As a function of?
His brother's age.
Okay. So in other words, Jose's age is going to be a function of his brother's age. In other words, Jose's age is going to be based off his brother. Does that make sense? It's kind of like how, with your sister, you say if she's this old, compared to her, I am this many years younger. So we're going to use her age as a reference. So what are we told here? Let's see. Jose is what?
3 times his brother's age.
Oh.
3 years younger than 3 times his brother's age.
Okay. So we'll start with 3 times his brother's age. So 3 times, it's always our input, right, that goes in. So it won't be J, it'll be his brother's age, which is
B.
3 times B, his brother's age. And then you said he's what compared to that?
3 years younger.
So would we subtract 3 or add 3? Yep. And that is the rule that would represent Jose's age. So now we say, wait a minute, what if his brother is how old? How old is Jose if his brother is?
5.
Oh, so now we take our rule. These are your favorite. We actually get to plug in. We say, what would happen if his brother's age was 5? Well, then we have Jose's age based off his brother being 5. And we set up our equation. And then solve. And this is the easier part. You're just doing some basic algebra. We're simplifying. 3 times 5 minus 3. So how old is Jose going to be?
12.
Yes, ma'am. Jose is 12 years old. So I thought he was going to be a lot older than that. I was like, oh, he's going to be 22, 25. Now he's 12. So what are some questions you have on that? Because that one was a little bit trickier.
Are they going to get shorter?
This next one's actually about the same length. This next one, though, is going to trip you up. I've already got a feeling. So what I want to let you guys do, I want to let you guys try number 6. Here's what I don't want you to do. Do not do this part yet. Don't do it. Don't plug in 12 yet. I just want the rule. See if you can come up with the rule for the situation. Do not plug that in yet, because we got to make sure your rule's right. So go ahead, guys, try number 6. This is where it's going to be we got to be very careful, guys, to read what they give us. R is the total rate M is the total miles. So we're going to have a function of rate based off miles. So you said, Shelby, that it's how much for the first mile?
$4.25.
Okay, that's for the first mile. On top of that, how much is it for each additional mile?
$1.50.
$1.50. Now, be careful. What does M stand for?
Total miles.
And what does 150 stand for?
Each additional.
Are these the exact same thing?
No.
No. What have we already accounted for?
The first mile.
So in other words, we don't attach M here. Give me a parentheses. We go M, but then we know it's not going to be total miles. It's going to be the total miles. Well, how do we represent those additional miles? What do we have to subtract from the total miles? What mile have we already counted?
$4.25.
Have we already taken into account the first mile?
Yeah.
We have to subtract 1 because what does M stand for?
Total miles.
Have we already counted 1 mile right here?
Yeah.
So we can't then put M over here because that would be total miles plus 1 additional mile. So what we do is we say, okay, if M is the total miles, we have to subtract 1 because, guys, that 424 is the first mile. You'd be counting 1 extra mile if you just put M here. If you just did M, that would be wrong. You'd be doing all your miles and then adding an extra fare onto that. That's what makes this one really tricky. You have to take off a mile because we're already counting our first mile. And M is your total miles. So now that we've got the right rule, I'm going to let you guys see if you can find out how much it's going to be for 12 miles. That was the tough part.
No kidding.
Yeah, here comes a little bit easier part. Just a little bit. So we set this up, plug in 12. We have 4.25 plus 1.50, parentheses, 12 minus 1. Remember, order of operations. What part of this do we do first?
You add or.
Whoa! Order of operations, PEMDAS.
Oh, no. Parentheses.
Parentheses, what's 12 minus 1?
It's 11.
Yeah,
My bad.
you're good. Be extra careful. Yeah. We got to do PEMDAS. You got to subtract that. And now, parentheses, we don't have any exponents. My dear Aunt Sally, my dear. That'd be multiply, wouldn't it?
Yeah.
So we're going to do 1.5 times 11. I'll let you tell me what that is here in a second.
1 second.
You're good.
16.5.
16.5. Perfect. And then we add those two together. $20.75. That was tough. I saved the most difficult one for last here. That was tricky. We had to take off a mile because we were already counting the first mile. What is it? So guys, let's flip back to page number 12. I'll let you flip to page 12. And here, you guys are going to get a little bit of an easier time, hopefully. Look at the top of this page. Shelby, what are we going to be doing here?
Evaluate each function for the given value of x.
Yeah, in other words, they're going to give you an input. You find out what the output is. So on number 1, check it out. Here's our function. What are we going to be plugging into our input? 3. So we're not doing f of x anymore. This is now a function of 3. So you plug that in. You do 4 times 3 plus 1. We'll see what you end up getting here.
13.
13, yes, ma'am. So your output was 13. Yep, it's that simple. So I'm going to let you guys try. Let's go numbers 2, 3, and 4 for me. Let's try these three. Go ahead and pause and try.
I don't even know if I got $3. I can just on it.
Let's check one we'll maybe feel a little bit better about. How about number 2? Yep, 2 times 5 is 10 minus 11 is negative 1. That's our output. So you could almost write that as an ordered pair. 5 was our input, negative 1 was our output, X and Y. How about number 3? So we have a fraction here. You always want to simplify everything on the top and then simplify everything on the bottom. So what's going on up top here?
I multiply 6 times 3.
Uh-huh.
I got 18, and then I added 3 there, and I got 21.
Okay, yeah, so 21 over 7. And hey, can that simplify?
Yeah.
Heck yeah, what does that reduce down to?
30.
Great job on that.
Oh, I actually got that right.
Heck yeah, you got that right. Let's go, that's our output. Last one here. This one's a little tricky. So we plug in 4. Now, if you have a fraction and you're multiplying a fraction to a whole number, do you know what part of the fraction this whole number goes to? The top or the bottom?
Top.
Yes. It multiplies to the top because could we almost put like an imaginary 1 under there?
Yeah.
Yeah, if you need to, guys, put an imaginary 1 under there. So 4 times 5 is going to be 20 over 2. Yep. And then here's where it gets a little bit easier. What do we know 20 divided by 2 will be? 10 plus 8. And you end up with, what do we get here? 18. Let's go. So we're able to topple these fractions. So last thing today, guys, and then we will be done with day 3. Unfortunately, this could be a little bit confusing. A lot of times it is for people. What are we going to be doing here, Shelby?
We want to learn how to find the domain from the function that we have in the equation.
Okay, we don't have a graph. We don't have a list of points. We have equations. How can we pull out the domain? Which, by the way, domain, what represents domains? Is that the x's or the y's? The x's, yep. And to give you guys a little reminder, an x, the domain is any x that gives us a solution, that gives us an output. Any input that gives us an output. That's what a domain is. Now, obviously, it has to give us a unique output. We can't have the same domain giving us the same output. Well, that raises the question, Shelby, what wouldn't be in the domain? Well, true, but if you have an equation, what's an answer we never want to get if you're trying to solve an equation?
0.
We're cool with 0. What do we call the 0 with the line through it, though?
I don't know. Undetermined?
Undetermined? How about no solution?
Oh, yeah, that.
Yeah, so here's the thing. What won't be in the domain? That's the question, right? What wouldn't be in the domain is the real question.
No idea.
Well, I know, that's what we're going to answer. It would be anything that gives us a no solution. Anything that gives us no solution. If an input gives us a no solution, we know it's not part of the domain. And what's the one number we cannot divide by that would give us a no solution?
0.
Yes! Guys, you can't divide by 0. If you see a fraction in this problem, you know there's a chance we could divide by 0. If you don't see a fraction, there's no chance you could be dividing by 0. That is what it all comes down to. We have to avoid numbers that could cause us to divide by 0. So look at number 1 for me. We're going to find the domain. Do you see any fractions?
No.
Nope. So that's my first question. Nope. Can you think of any number, Shelby, that if you plug that number in for x would cause us to divide by 0 or get no solution?
0.
What would happen if you plugged in 0? What's 5 times 0?
0.
Plus 6.
Yeah.
That'd be 6, wouldn't it?
Yeah.
Hey, we're cool with that. I don't think there is a number that we could plug in that would give us no solution. You could plug any number you wanted to in for x and it would give you an output. We don't have a fraction where we're dividing by 0. So do you know what your domain would be here? If every number works, if every x is possible?
5. And
Remember how we represent every number?
infinity sign.
Yeah, negative infinity to positive infinity. Absolutely. How about, this next one, number 2. What do you notice we have here?
A fraction.
Yes, we have a fraction. Actually, on these last two, both of them are fractions. So here's the question. If you have a fraction, is there a chance you could divide by 0?
Yeah.
Yeah. And what part of this fraction are we worried about that would cause it to divide by 0? The numerator or the denominator?
Bottom one.
The denominator. Yeah. Yeah, guys. What do we know this denominator cannot be?
0.
Can't be 0. X minus 8 cannot be 0. I'm going to bring that down. Let's write this out, guys. We know x minus 8 cannot equal 0. If it does, you're dividing by 0, which is not allowed. That's a no solution. So let's solve this. We got a little equation here. Let's solve this for x. What would you do to get x by itself? Maybe add the 8 over. So then, what's the one thing x can't be? 0 plus 8 would be?
8.
Oh, because what would happen if x was 8? What's 8 minus 8?
0.
Oh, that's why. X can't be 8 or else you're dividing by 0. Is that the only number that would cause that to happen?
No. Sure. Yeah.
Yeah, there's no other number, right? No other number minus 8 would give you 0. That's the one thing that x can't be. This is the one thing not in the domain. So in other words, every other number works. So our domain would be, check this out, everything from negative infinity up to, what's the one number we can't include?
0. 8.
8. We put a parenthesis. Why do we put a parenthesis instead of a bracket there? Would it be an open or a closed point if we can't include it?
Open.
Open. So parenthesis. Then how do we jump over a point? We put a U. Yeah, give me a U-turn there, and then another parenthesis. And now we're jumping over 8. So what this shows here, Shelby, we stopped right before 8, then we jumped over 8. And then where can we head to now?
Positive.
Yeah, every other number works. Look at the difference between these two. These are almost identical. We just had to make a special exception, didn't we? 8 was the one number we couldn't include. So I'm going to let you try number 3. And then I'll give you a few problems to do for homework, and we'll be done for the day. So try number 3 for me, guys. Let's take a look. So do we have a fraction on number 3, Shelby?
Yes, we do.
Yes, we do. What part are we worried about? The numerator or the denominator?
Denominator.
We cannot divide by 0. That's in the denominator. So what cannot equal 0 down here? What do we have?
5.
If that ends up equaling 0, we get a no solution. We would end up with an input that does not give us an output. Let's find out what x can't be. That's what we're doing right now. We're finding out the one input that doesn't work. So let's solve for this equation. We got a 2-step equation here. What would you do first? Subtract 15. And then last step.
Divide by 5.
So x cannot be
Negative 3.
So just like 8 was the one thing that couldn't be in our domain on the last one, now -3 is the one thing that can't be in this domain. Every other number works.
Oh, so you're basically just turning that into a two-step problem?
Yeah.
Oh,
And then guess what? Our answer is going to look identical to this one, except instead of 8s, what are we going to have in the middle?
-3.
We're going to replace 8s with -3 on this one. Yeah, it's the exact same every time, guys. Negative infinity to -3, unioned with -3 to infinity. Just like the last one, we're just replacing, or we're just mentioning the one thing that x cannot be, the one thing that would give us no solution. Your domain is everything but -3. So your homework, guys, is going to be 1, 2, and 3. So if you can get those done before you come to class or before our next day, that'll be fantastic. Thank you very much. Go Jumpers.